Bienvenidos al ciclo de conferencias de investigación Universidades por la Ciencia, organizado por Fundación UNAM, el Colegio Nacional y el conjunto de universidades y centros de investigación del Consorcio Universidades por la Ciencia. Les agradecemos mucho el interés y que nos acompañen. Y el día de hoy tenemos una conferencia muy especial a cargo del doctor John Adams, quien es el director adjunto de una de las centros de investigación más fascinantes, Biosfera 2, en la Universidad de Arizona. Le agradecemos mucho al doctor Adams que acepte esta invitación por esta conferencia. Welcome to the seminar series of the Universities for Science Consortium, organized by Fundación UNAM, Colegio Nacional, and the universities and research centers of the Universities for Science Consortium. Welcome, thanks for joining us. And today we have a very special conference by Dr. John Adams, who is the Deputy Director and the Chief Officer of one of the most unique research facilities, Biosphere 2, in the University of Arizona. Thanks, John, for accepting this invitation. This is a really very interesting presentation. And as we have been talking a few minutes ago, Biosphere 2 is a rather unique research facility. It permits to conduct experiments at a very wide range of temporal and spatial scales. And the relevance, the importance of Biosphere 2 continues to grow. Is now with the climate change, the affectation of all the ecosystems we are producing, the need to fully understand the deep interconnections between the geosphere, oceans, atmosphere, the Earth's interior, and the biosphere is more important than ever. Nos acompañan en el panel el presidente de Fundación UNAM, licenciado Dionisio Meade, la directora ejecutiva de Fundación UNAM, Araxi Rodríguez, la presidenta del Consorcio Universidades por la Ciencia, Araxi Urrutia, y el doctor Constantino Macías, quien es el responsable de la unidad UNAM Canadá y quien es uno de nuestros más distinguidos investigadores en el Instituto de Ecología, ha sido su director y actualmente también es parte del board de la unidad Biosphere 2. Thanks very much, Tino. Nos acompaña también en el panel el doctor Constantino Macías, quien es el que lleva el Centro de Estudios Canadá UNAM y quien es uno de nuestros mejores especialistas y que nos ha acompañado en los programas que hemos estado transmitiendo, incluyendo el ciclo del Antropoceno. Muy bienvenido, doctor Macías. Dr. John Adams has a very long experience working in Biosphere 2. John is the person who better knows the research experiments being conducted in Biosphere 2, and has been the one responsible for what we have now and at the Biosphere 2. John started a long time ago studying the increasing CO2 in the different systems we have in the biosphere. And the biosphere is now increasing the research capabilities, focusing on the new experiments in the different ecosystems, including the oceans with the coral reef, the tropical forest, the deserts, so the rainforest. So it's privilege to have John today. We welcome you comments, questions, and thanks again for joining us. And John, Constantino, Araxi, and Dionisio, thanks very much. And we will look forward for the conference by John Adams. And we can make additional comments later on. Well, the floor is yours. Thanks, John.
Okay. Well, thank you very much for everybody who's on. Thank you for the opportunity to share with you Biosphere 2. Just before I share my presentation, as was mentioned, I've been with Biosphere 2 29 years. And so I came in at a time when it was transitioning from people living inside, which I'll talk a little bit about in my presentation, to one of the world's largest earth and environmental science laboratories of today. And so what I will do is I'm going to share my screen. Go. I want to make sure everybody can see that okay.
Okay.
Great. All right. So I think, one of the things that we have really strived to look at is, Biosphere 2 is one of the world's largest controlled environments that's dedicated to understanding the impacts of global climate change, but it didn't always start necessarily with that exact focus and mission as we have today. And I think, all of us on this call, we're always looking from Earth out into space. I think very rarely do we actually, none of us really have the opportunity to have this perspective unless you're an astronaut. But this is the really important one because we need to understand Earth systems. We know that it is constantly changing. We know that what we are doing have significant agents of change on Earth, and those changes impact the resources that each of us are dependent on. But how do you really begin to study Earth systems and all of its complexities? And there's tremendous amount of work that's happening around the world at various institutions to try to unlock some of those key factors and mysteries. But I think, again, what many people sort of think about when they hear Biosphere 2, because of its early history, was this idea of a futuristic colony for the moon, or more recently, we hear lots of conversations about going to Mars. And not to take anything away from any of those who are heavily involved with the space sciences that are on this call. But from my perspective, I think it's a very long time away before large numbers of people are going to be able to travel off of this planet. And we are going to be here, and we need to understand how our planet is changing, because if we're not able to adapt, we're not going to be able to survive. And so as much as we like to romanticize about getting back to the moon, which I think is a very real possibility, going to Mars, which I'm not an expert, but a lot that I've understand is that, that's going to be a one-way ticket right now. We're not quite sure on how we're going to shield ourselves from radiation, get there and set up a colony. And although Biosphere 2's headlines, and for many people, they think of it as this futuristic colony, that was not the fundamental reason why they built this facility here that you see in this image. And one of the fundamental reasons really started with a guy by the name of Claire Folsom and others, but can we actually capture varying types of biological processes inside of a controlled environment, and to be able to understand them very specifically and precisely? And so Claire Folsom, we actually still have some of his bottles that are on the order of 40 and 50 years old, where he took seawater, for example, and a little bit of algae and plugged them up. And we think of them as terrariums. Most of us probably have small versions of those, like that one on the left-hand side of the screen. But again, those give us insight, but they're not overly complex. And over time, we have seen various researchers. This is an image of BIOS 3. This was a Russian experiment in the 70s where they were looking at closed systems and how one can survive inside of that closed system. And for example, you see in the lower right-hand corner, grow food and use that biological activity not only for nutritional needs, but also to help balance the atmosphere. For example, the CO2 that this particular person will expel and the oxygen that is needed being given off in part by the plants. And, can we find a balance? Something, again, that we often know happens on Earth, but we take for granted. More recently, something that's very famous, and I think, 3 or 4 years ago, they completed just a little over a 1 year stay. But this is an image of the Chinese Lunar Palace in Beijing, China. And so this is another facility where you have people living inside for an extended period of time and trying to grow their crops. And again, the idea is can we use our refined understanding by doing experiments like that here on Earth to eventually allow us to establish a long-term colony at another location, for example, the moon or Mars. But the thing that these facilities have and what they don't have is that when you look at Biosphere 2, we're talking about a structure that is roughly 1.27 hectares under glass. BIOS 3, the Russian experiment, the Chinese Lunar Palace, they are significantly smaller in size and in complexities. And so there was a group of people who wanted to better understand how the Earth works and functions. And so they felt the only way that they could achieve that was by building and bottling up some of Earth's systems. And so they embarked on a journey to build Biosphere 2. And that began in the late 80s. And the construction was completed in 1991. And inside of Biosphere 2, they tried to incorporate and capture as much biological diversity as they could, but with the understanding that there was going to be constraints in which they would be able to control the conditions inside. And so everything that you see listed here, they can all, from a climatic perspective, can be lumped into, what we call tropical or subtropical systems. And so even though vegetatively they are very distinct systems, they are and do share some of the very similar climate states and conditions. Now, they started and put on the northern end of the structure a tropical rainforest. As you move down from the rainforest to the south in the structure, you have a subtropical savanna and thorn scrub. You have an ocean system, a mangrove system, which is labeled as a marsh here, and then a desert, which is a coastal fog desert. And these systems here, I like to collectively call as our wilderness systems. And we still use that term today when we refer to this particular area of Biosphere 2. And I think some important things to note is that the ocean was originally stocked with organisms, corals, and really anything that they could capture off the Yucatan Peninsula of Mexico. So a lot of those organisms originated from there and brought here. The thorn scrub, for example, is a subtropical thorn scrub, and some of that vegetation was actually collected. And I'm here in Tucson, Arizona, which is not very far from the Mexico border, but many of the plants that ended up in the thorn scrub were actually collected in northern Mexico, about 2 days' drive from Tucson into Mexico. The coastal fog desert, which is listed here as a fog desert. Fog deserts are those regions that you find on the western, typically the western edge of actually all continents. It's in an area in a latitude where you will have temperature differentials between the ocean and the land mass, which then oftentimes will result in the generation of fog, and the plants that live in these regions are specially adapted. Our particular desert, our coastal fog desert, is not the Sonoran Desert that you find around Tucson, Arizona, where Biosphere 2 is located, but actually this fog desert that you find down on the Baja Peninsula of Mexico. And in fact, many of the plants there were also collected in Mexico. The marsh system is a mangrove system that you would find off the coast of South Florida, for example. And the trees that make up our mangrove system inside were actually collected from an area that was slated for development. And so they collected as much of the root ball, as much of the soil and biomass in that area, water, crated them up and brought them here to the facility and transplanted them in. Now, the area over to the left, which is labeled intensive agricultural area, this area was a space that was specifically dedicated for those who were living inside Biosphere 2. In September of 1991 is when they were sealed inside. This is where they grew their agricultural crops. And so this area today has changed very dramatically, and I will talk about that a bit later in my presentation. And then finally, they weren't roughing it when they were inside. They actually had an area that we refer to as the human habitat. This is where they had office, laboratory spaces, they had a workout area, they had an analytical laboratory, and they had their apartments, their kitchen, and their dining area. Now, I think this is probably the image that many people associate with Biosphere 2. The sealing of 8 people inside of Biosphere 2 for nearly 2 years. So they were sealed inside Biosphere 2 on September of 1991, and they did not come out until September of 1993. And from my opinion, this initial experiment was overwhelmingly successful. I mean, they had done something that no one else had ever done. They had actually created a larger than anybody has done, controlled environment that was completely isolated for the most part from the outside environment. Its leak rate, for example, only was 10% per year of that entire volume. And that facility's leak rate, for example, depending on what module you have connected to the International Space Station, would rival that. Now, inside the facility, they would do an intensive agricultural biome. They set aside that space to grow all of the food that they were going to need when they were sealed inside for those 2 years. And although that system was extremely successful in producing agricultural crops for them, one of the challenges that they did find is that the soils they put in that agricultural area and the soils that they put in the rainforest, they had to recreate to the best of their ability. And so in creating them, they intentionally created soils that were extremely rich in organic material to support the intensive growth that was going to happen over that 2-year period. They wanted to make sure that there were not nutrient limitations for the crops that they were going to be dependent on for their nutritional intake. But in doing so, what they created was an imbalance between that which was happening in the soil and the atmosphere, because they had hoped that these biological systems would balance one another and the plants would take up the carbon dioxide that was being expelled not only by the humans, but also by the soil organisms. And then that photosynthetic process, the breaking down and taking in of that CO2, the splitting of water and giving off oxygen would be enough to sustain those people that were inside at levels that were suitable. Well, as you can see from this graph, that day 0 is the time that they close the door. And as we get and approach day 500, you can see that oxygen percentage dropped down to 14.2%. It was at this level that the team that was managing what was happening on inside and in constant communication with those 8 people who were sealed inside made a strategic decision for the health and safety and well-being of those 8 individuals to add oxygen in the system. And why you see it jump up on day 500. They added it in to bring it back up to levels that was not potentially going to be harmful to those that were living inside. Now, again, in my opinion, the mistake that they made is this was an experiment. No one had ever done anything like this. I mean, all of you who are on this call know the reason that we do experiments is because we want to learn something new. And in fact, if we do experiments and they simply confirm what we already knew and we don't learn anything new, yes, we've had that confirmation. But again, we get much more, in my opinion, when we have these types of new discoveries or we're doing things that we don't know ultimately what the outcome was going to be. And that was Biosphere 2. But they were not forthcoming with what had happened inside Biosphere 2 and the fact that they had to add oxygen back in. And it was only after they received many inquiries as to the fact, did they actually add oxygen back in, that they retracted some statements. Those statements were originally, no, they did not. They then admitted that they had to, but it was after the fact. And they were not forthcoming. And as a result, that they lost a tremendous amount of integrity and credibility with not only with the scientific community, but the media and the public. Now, one of the things that was happening inside Biosphere 2 that ultimately led to I think its repurposing is exactly what you see happening in this equation up above. And so what was happening is that inside Biosphere 2, when they constructed it, there were large amounts of concrete throughout the facility. And so when you have higher levels of CO2 and you have calcium hydroxide, this is this newly formed, still curing concrete, what happens is you're going to have a reaction. And so that CO2 is actually being bound and partially being bound to create calcium carbonate and a little bit of water. Well, when they brought in some atmospheric and some geochemists to help them better understand why was oxygen going down at one rate, but yet CO2 was not getting as high as they had originally anticipated inside, what was happening? Because they have a sealed system. Where is it going? And so they brought in a guy by the name of Wally Broecker, a world-renowned geochemist who was originally from Lamont Doherty Earth Observatory at Columbia University, and a graduate student of his, a gentleman by the name of Jeff Severinghaus. And they were brought in to try to figure out what was happening. They couldn't balance their equations. And ultimately, what they were able to do is to unravel what was happening. Not that this is earth-shattering. People know this equation. This is very well documented. But in the context of what was happening inside Biosphere 2, it wasn't until Dr. Broecker and Dr. Severinghaus put it together, published a paper, and it was at that moment, and I actually had conversations with Dr. Broecker where he said, that was the light bulb moment, because they could trace molecule by molecule where things were going, how they were reacting, where they were being stored, and how they were influencing the atmosphere at a scale that was not previously available outside to them. And so they viewed it as an opportunity rather than having people live inside as an Earth and environmental science laboratory. And so although there was another mission inside Biosphere 2 after that first one concluded, and again, remember that was for 2 years, the second mission was about 6 months. Then in early 1994, there was a shift. And there was a focus to use it as a research laboratory for understanding the impacts of global climate change rather than having people live inside. They stopped having people lived inside and began focusing. And I think this picture illustrates, I think, a deficiency in sciences as a whole when we look at Earth system science. We have invested tremendous amounts to understand the fundamental building blocks. What is an atom? Conversely, we have looked at and developed and continue to develop very sophisticated telescopes. We have put them on remote mountaintops in conjunction with one another. We've deployed them in space, all with the desire to look to the ends of the universe and to see what is out there. But in my opinion, we have not built a tool equivalent to what you see with the Hadron Collider and, for example, this giant Magellan telescope that allows us to understand Earth system. And as I started off my presentation, Earth systems are infinitely complex. We still understand very little, and we know that they are changing as a result, in part, by what we are doing. And again, we want to be able to better understand those changes because ultimately those changes impact resources that you and I and everybody else depends on. And so Biosphere 2, and again, from my assessment, is the collider for Earth sciences. And so it allows us a much closer look at how some of these systems are behaving. Now, remember what we put inside Biosphere 2, and we made this mistake early on with Biosphere 2's history because the folks from Columbia University who initially took over the management and started experimenting inside Biosphere 2 referred to our rainforest or our ocean or our desert or our mangrove system as analogs. Again, it's my opinion that there is no true analog to Earth systems. Earth systems are infinitely complex, and no matter how smart we think we are, how much we learn, we will never be able to truly replicate Earth systems. We can capture some of those fundamental components, just like we've done in those small flasks that Claire Folsom did, or just like we've done inside Biosphere 2, but it doesn't represent all aspects of Earth systems, but it does offer, an example in a facility like Biosphere 2, a complexity that finds what I refer to as middle ground. So many of you probably recognize and have maybe even worked in mesocosm facilities. And some of those mesocosm facilities, range in size from growing plants in pots like what you see here to chambers that are 1 meter or 2 meters square. Conversely, I'm sure that a lot of you work outside in natural systems. And so we all have experience working at field sites. And we know that there is a tremendous amount can be learned from these field sites. And some very meaningful experiments and observations have been done. But it's primarily that. It's primarily observations. We don't typically have the ability to control the weather or to manipulate the conditions. We can do exclusion experiments where we can exclude as much as we can the rain. We can do phase experiments, free air CO2 enrichment, where we can add CO2 to a given area. But for the most part, we are still subject to lots of natural variability. Where Biosphere 2 comes in is it's in this middle ground. It's a scaling tool that is in between these very precisely controlled laboratory experiments and these field observations that we make. And that is the critical role, from my perspective, that Biosphere 2 presents for the world as a whole. Is it's at this middle ground with these very complex systems that now have been in place for nearly 35 years in most cases. And so what we are looking at doing and focusing on here at Biosphere 2 as a whole is looking at the impacts, for example, of water and how water's availability, primarily in these subsurface processes, change over time as a result of land use change and climate change. We have this large tropical rainforest system, and we'll talk about some experiments that we've done inside of there. It's 44 meters on a side, and its tallest point is 28 meters. We have an ocean system. This ocean system that you see here is nearly 2.6 million liters of salt water. And it is, for example, 7 meters deep on the far end. And as you proceed into the foreground near us, it has a reef and then a shallow lagoon and ultimately up onto a beach. We've done some incredible experiments inside of there, which we will talk about. And outside Biosphere 2, we're continuing to see an advancement of sciences where we're looking at how do we co-locate vegetation and, for example, renewable energy and realize a benefit for both of those. So when we look at inside Biosphere 2, this space that you see here in this image is representative of what we call LEO, the Landscape Evolution Observatory. This was not originally part of Biosphere 2's construction and is the University of Arizona's institutional experiment. What the University of Arizona did when they assumed management of Biosphere 2 in 2007 is they saw a unique opportunity to do experiments inside Biosphere 2 that couldn't be done anywhere else. And that is the key. If you're going to do experiments in Biosphere 2, let's use its unique attributes to do things that we can't do anywhere else. And so they saw an opportunity to basically change the look and the structure and function of that intensive agricultural space where the biospherians originally grew their crops to what you see here. So you're looking at a slope that has volcanic basalt on it. It's 330 square meters. The soil depth is a uniform depth of a meter, and it is designed to replicate a zero-order catchment. LEO is the largest indoor earth science experiment, and fundamentally, its purpose is to understand the fate of water in semi-arid environments. It rains in the mountains, how much water ends up downstream for you and I to use, and what impacts the quality of that water. What you can't see is that embedded in this soil is nearly 1,800 sensors and samplers. The volcanic material was chosen because geologically it's relatively young. It weathers very quickly. And over the 9 years that we've been running this experiment inside Biosphere 2, we've been seeing over time and increases in complexities. We've seen an increase in nutrient availability as a direct result of the weathering of the material that you have here. And we're actually now at a point where we anticipate putting a vascular plant community onto the slopes of what you see in front of you, now that we've had an opportunity to look at it and what I refer to it as a relatively more simple state. So think of it, we've unstitched the biological and the physical worlds with LEO, and now we're going to stitch them back together. And so this gives us a great opportunity to help improve the models that we use primarily to predict subsurface flow. The great thing about LEO is you can change the amount of precipitation that goes on the slope. You can label that precipitation, for example, with deuterium or lithium chloride or lithium bromide, and you can look at how this entire system behaves. What you can't see is this entire slope sits on 10 load cells. And so it's the world's largest weighing lysimeter. We know exactly what the weight is. We know how that weight changes. And in fact, these load cells are so sensitive that we can detect as little as a cumulative 2 millimeter water surface change over the slope. We have above ground instrumentation, which you can see in the foreground of this in this tower. You might be able to see sort of on just on the left-hand side of that tower that's running the length of the slope is a track. That track carries an infrared and a hyperspectral camera. And so we're continuing to conduct experiments on here, and we're very excited to be adding this vascular plant community here later this fall is the anticipated time frame. Now, I talked a little bit about, but you're looking at our ocean system. So inside Biosphere 2, we have a large research tank. Its volume is 2.6 million liters of salt water, originally modeled after a Caribbean reef environment that you find off the Yucatan Peninsula. And early on, some of the most significant research, in my opinion, to come out of Biosphere 2 came out of research directly from the ocean system. And we were one of the first places to show that as you increase atmospheric CO2, you see this change in carbonate chemistry in the water profile. So CO2 plus water becomes carbonic acid. That carbonic acid reacts with a carbonate ion that's readily available in the ocean column to become two bicarbonate molecules. It's in this bicarbonate form that is no longer readily uptakeable by things that calcify, for example, like coral or mollusk. And although you do see a pH drop, you also see this very dramatic change in nutrient availability. So Chris Langdon and others were one of the first to show and directly correlate increasing atmospheric CO2 with decreasing coral calcifications because of that carbonate ion availability reduction in the ocean column. Today, what we're doing is those orange buoys towards us or towards the screen. We are now going to be adding and renovating the system to add a new light field over it. We're going to be adding beams, trusses that are going to support a light array. The reason we're doing that is we don't want to light limit or light stress this next round of corals that we're going to put in our ocean. And what we've also done is we've upgraded our ability to heat and cool the ocean. So we can actually take this 2.6 million liters of gallon and we can start at 25 degrees C and we can heat it up in 2 degrees C increments over a 24-hour period, all the way up to, if we want to, nearly 38 or 40 degrees C. The reason we want to do that is what we see happening in most reefs around the world is, yes, they're impacted by nutrient overloading. They're impacted by the reduction in the world's pH and this decrease in carbonate availability. We see damage as a result of nutrients and other things. But one of the primary drivers for bleaching that we see around the world is this increase in coastal water temperatures. For example, off the coast of Florida, last year, we saw temperatures that were nearly 40 degrees C. Corals just can't survive that. If you look at Hawaii, they attribute much of the bleaching and that 50% loss that we see, for example, in Australia on the Great Barrier Reef, primarily has been attributed to this increase in coastal water temperatures. The same thing, for example, in Hawaii. But what we do see is, although you see the coral on the right is dead, the coral on the left has survived. What attributes does it have? And so what we're doing is actually working with a number of different groups. We have partnerships with over 52 institutions. But what we're going to use the Biosphere 2 ocean, once we get the light over, is to actually test the thermal resiliency of many of these corals. And are there certain genotypes that show greater thermal resistance? And we know that they've been identified in the lab. And what we're going to do next is introduce them into the Biosphere 2 ocean and take them through a series of temperature regimes in a system that doesn't just have a lab setting in a small chamber or in a small aquarium, but has algae, has fish, has invertebrates. It's more representative, but again, I don't want to lead anybody that it's just like or it's closer to a natural community in many respects. And so to begin to test some of these ideas, and can we actually harden corals? How well do they do? And what is their thermal resiliency? And that is going to be some of the fundamental experiments that we will begin at the beginning of 2026 or 2025, once we complete the installation of these lights, which actually will take us the remainder of this year. And we should be ready at the beginning of next year to do that. Dr. Diane Thompson, who is the director of research in this area, is leading that initiative. One of the other areas is we heard a little bit about our tropical rainforest system. This system, over its history, again, remember it's been in place for nearly 35 years, has been one that has been used for a number of different experiments. One most notably is there was a prediction by a model, the Big Leaf model, that suggested that once we reach an atmospheric CO2 concentration of about 600 parts per million, we're going to see the net ecosystem exchange of areas like a tropical rainforest here become saturated. And so, regardless of atmospheric increases in CO2, we're not going to see a net gain in carbon uptake by these tropical systems. Well, how do you test that? You can't just stick a dome over a tropical rainforest system as much as we would like to. Yes, you can do experiments where you can add CO2, but oftentimes you're subject to a lot of those natural variabilities. But in our rainforest, we can control all of those conditions. And we have nearly 100 species that are interacting with one another, both above story and below story species. And we raised and lowered our CO2, and we found that our system, just as the model predicted, saturated at 600 parts per million. We've also done experiments where we've looked at thermal tolerance. The Biosphere 2 rainforest, because it's under this glass shell, is probably one of the warmest rainforests in the world. That also gives us an opportunity to look at the thermal resiliency because we know tropical systems are getting warmer and drier. So our teams actually raised and lowered the temperature, and we found that there's a lot more elasticity in the thermal tolerance of many of these tree species than we originally gave them credit for. And that was recently published in Nature Plants. And the most recent experiment we did is this was a large collaboration with folks from the European Union across the US. And what they came in and did is they collectively wanted to understand how carbon, energy, and water cycling changed as a system went from a very wet, unstressed state to a very dry, stressed state. So they gave this system a 70-day drought, and they called it WALD, which was in German, which was Water, Atmosphere, and Life Dynamics. Our partners there were at the University of Freiburg, among a number of other institutions across Europe. But they descended on the Biosphere 2 rainforest, nearly 100 researchers, everything from undergraduates to graduate students to postdocs to senior research faculty, came in and they heavily instrumented this rainforest, looking at not only what was happening at the leaf level and the soil, but what was happening in the upper and lower canopy. Brought in nearly $5 million worth of instrumentation, got it completely set up inside the rainforest of Biosphere 2, made sure everything was monitoring and recording, and then they were able to stop the rain. And over that time frame, at various intervals, they were actually able to label the atmosphere to more precisely trace with carbon-13 where was it being taken up and by which plants and where was it being stored in the stem and the leaves at the very top. And so this has resulted in several papers, one that was published in Science and one that was published recently in Nature. And there is a whole suite of other papers that are slated to come out here towards the latter half of this year and next year. But this was a very exciting experiment, and I think illustrates the power of Biosphere 2 is a multi-user institution to do very unique experiments. And this group at the University of Freiburg approached us because although they were doing a number of experiments outside in natural systems, they couldn't do these very precisely controlled experiments that they desired to understand some of these fundamental mechanisms in the exchange of energy and carbon and water between the soil, the atmosphere, and the plants. And finally, one of our large initiatives, and I think at some point later, you're going to hear from a colleague of mine. His name is Greg Barron-Gafford, but that's the growing of different types of agricultural crops or plants amongst or underneath solar panels. And this is referred to as agrivoltaics. And the significance, although it's not happening inside Biosphere 2, is this science was actually started or reinvigorated here at Biosphere 2 by Greg Barron-Gafford. Although it originated in Germany in the mid 80s, is my understanding. There had not been a lot that was done up until Greg really started looking at this co-location in very arid or semi-arid environments where you have extremes in temperature. You typically don't have light limitations. And so we've been able to expand that science to now incorporate facilities that are in Mexico, that are in Israel, that are in Morocco, that are in different regions within the US. And so those partnerships and this type of research is expanding because, for example, here in the Southwest, what we see is when you go grow plants underneath those solar panels, at a minimum, you see the need for water by those plants underneath the solar panels reduced by 50%. The transpiration by the plants actually cool the panels to decrease their overall temperature. And so it's a mutual benefit. And I'm taking what Greg says, Greg Barron Gafford, he's the faculty who oversees that project. He's using the land twice and harvesting the sun twice to produce energy and to grow food. Now, one of the things that we're doing at Bias for Two is we have this new large shipping container that was converted into a vertical farm. You can see indoor pictures here of it. And you're looking at a facility that is highly productive. The challenge is it does a great job at water conservation. It doesn't do as good a job at energy conservation. In fact, it's probably an energy hog, primarily driven by the lights and the need to control the conditions inside to grow the leafy greens that you see on that wall. And what we're going to do is actually now we're in the process of finalizing our engineering drawings, but we're going to actually connect an agrivoltaic system to the freight farm, that indoor shipping container. And the benefits is now the solar panels are going to provide the electricity for the indoor vertical farm. The shade on the outside is going to provide an environment, and essentially it's a controlled environment, obviously not as precisely controlled as that you have inside of that shipping container, but it's going to allow us to grow taller statured crops because inside what you saw hanging on those walls is primarily leafy greens. We're not going to be able to grow these traditionally fruited plants like tomatoes or potatoes or carrots or strawberries. And so those things can be grown outside, but inside you can grow some of those leafy greens and more sensitive crops. And so you essentially have the best of both worlds. And our goal is that we want to be able to close the energy and the water budget because we plan to harvest water not only off the solar panels through the various rain events that happen here regionally, but also using a technology from a company that's located just to the north of us where they extract water from the atmosphere. And so we believe that if we're able to actually successfully achieve this, we will be one of the first to actually be able to show and have a system that grows agricultural crops inside and outside, but is completely off the grid and not dependent on a continuous water source. So we're very excited about that. In conjunction with that, this area also has several greenhouses, and the significance of these is they're not just greenhouses, but the material that's coating those greenhouses has a special component that's incorporated into them that cuts out all wavelengths above 800 nanometers. And so 800 nanometers is that wavelength that typically is going to create significant amounts of heat inside of your greenhouse. And so if you can exclude it, but allow that 400 to 700 nanometers that you need to grow the plants, your energy consumption is going to be needed. It's going to be less. And so the idea is how do we optimize the efficiency of these types of greenhouses? This will all be in a complex as you see here in this illustration. In fact, the greenhouses are already built. The freight farm or the shipping containers, they're already there. And again, we're just getting ready to build out this agrivoltaic system. And so this will be a place where students and others can come and see side by side these types of opportunities to grow crops in different conditions and in different areas and in conjunction with different technologies and realize the advantages that people have when you do so. The final project I'm going to talk about before I conclude my presentation is one where the facility that you see in this rendering over on the left-hand side, this is referred to as the test module. So back to the original history of Bias for Two, before they built Bias for Two, they built several prototypes, of which this is the most recent one, to test the engineering, the design principles before they built a larger Bias for Two facility. And although it was used initially to do some testing, there hadn't been much use for it in these latter years until one of our research directors by the name of Kai Stotz came along and saw an opportunity to create a hermetically sealed environment on a much smaller scale. And there is a need scientifically, because when we think of organizations like NASA here in the United States, we think that they should have a facility like this. They actually don't. There are very few hermetically sealed environments that allow or are dedicated to understanding how you transition from traditional mechanical devices or physiochemical things like what they have on the International Space Station to using bioregenerative life support systems to support the people who are inside of that. And so SAM, the space analog for the moon and Mars, is one of the first facilities here in the US that is designed to be completely hermetically sealed. Although there are a number of analogs around the world, the only other one that we know is hermetically sealed is one in Poland. But even the High Seas Project, the one that has recently been widely publicized, that's run by NASA and has people staying, those are all open air. And so part of SAM, what's exciting is that you also have an opportunity. We have spacesuits. And so you can actually now start to do experiments that can only be done in a facility like this. And what you see listed here in these bullets are some of the major research emphasis that we looked to do inside of SAM in the coming years. We've just completed construction and modifications on it. There is a bit more to do, but up to this point, we've actually had 3 teams stay inside of that facility for about 7 days each. So 6 nights and 7 days. They have stayed inside of SAM, and it continues to be a success. And we are continuing to get inquiries for a wide range of teams to come and utilize SAM and its unique characteristics and attributes that it has to further that research. And so SAM really sort of goes back to the original roots of Biosphere 2, or the perceived roots by many people of Biosphere 2. This is one of the things that tied to it, just like Biosphere 2 is designed for model validation and calibration, along with SAM, and you can actually look this up on National Geographic's website. If you just do a search for CMOC, SIMOC, this is actually a model that you can go in and model your closed community. We've also integrated a module as a part of this application that models Biosphere 2 as well. So you can model an off-world community, or you can model Biosphere 2, but it takes into consideration 30 years worth of plant science data that NASA has produced in all their cultivars, and looks at the growth cycles and how oxygen consumption can be offset, but then when other devices would need to be brought back online, and how that impacts, for example, the overall conditions inside as well as your energy consumption. So this was a great exercise, and I've done this with middle school to graduate students, and everybody gets a tremendous amount out of it. And it really begins to give you a much better understanding of how these closed systems work and how dependent we are, and how slight changes can have very dramatic impacts. So this is a short video, or this is a short video of Biosphere 2 that's going to show just some of those features that I mentioned, and some of the things on the outside. But again, this concludes my presentation. I think, yeah, we're just a few minutes past 45 minutes, about 50 minutes. And now what I'd like to do, once this concludes, is open it up for any questions that folks have. I'd be happy to answer those as we look to the future and use Biosphere 2. So thank you very much for this opportunity.
Thanks very much, John. It's a very interesting presentation on this unique facility, and thanks for the video. It's really interesting to see. It's like a virtual tour of the Biosphere 2.
No, you're welcome. And like I said, if there are any questions, I'd be happy to answer those.
Yes, we actually have a lot of comments and questions. Thanks very much to all for joining us. We will take as much as we can. We have many congratulations for this presentation, and comments about the capabilities of Biosphere 2 from many different places. Thanks also to the students, and including the postgraduate students in US, Canada, UK. Thanks for joining us. And we have questions related to the construction of the of Biosphere 2. One is why was this location in the Arizona desert selected?
That's a great question, and one that we're often asked. So I think, I'd love to give you a really sort of sophisticated answer. I think fundamentally for them, when they were looking at sites, this, at sort of its foundation, the property was available. But also when you look at Southern Arizona, and they were looking to build a large, essentially a greenhouse, they were going to leverage external light for the driving of photosynthesis inside. They didn't want to have to supplementally light it. Southern Arizona gets about 300 sunny days a year. So having all of that light, not having a lot of cloud cover, that was advantageous. Also, this particular region, just outside of Tucson, Arizona, geologically, it's very stable. So we don't get earthquakes or anything. So when you're looking to build a large glass structure, that was a consideration that, and a feature that they felt was important. And then also this particular area, we don't get a lot of really violent storms like other parts of the world may, or for example, even the central United States get, where you have the cold air masses and the warm air masses interacting with one another and creating, for example, tornadoes or thunderstorms that generate large hail. We are fairly insulated from those types of things. Yes, we do get some violent storms, but not to the extremes that, for example, the Midwest or other parts of the world may experience because of our regional location. So really, it was those three factors and the fact that Biosphere 2 is situated between two major universities here in the United States, and that is Arizona State University, which is only about an hour and a half to the north of us, and then obviously the University of Arizona, who is the managing institution and has been since 2007. They're only about 50 minutes to the south of us. And so it was all of those factors that contributed to the building of Biosphere 2 in its location that it is today.
Yeah, it's a very special place and great having a Biosphere 2 there. There are questions well mentioning that it's a huge research facility. They ask how are the inside conditions controlled, and in particular, they ask about the sunlight. I think they were impressed by the
yeah,
the windows.
So to answer your last question first, how do we control? So we are not able to control the sunlight. So we are subject to the light regimes that you experience at our latitude here in Southern Arizona. So we really can't do much to control that inside Biosphere 2 proper. But what we've seen is because of the number of sunny days of year, and if you look at the total light that we receive over the course of a day, those moles, those micromoles per meter squared per second, that when you integrate that underneath and you look at that curve, we receive inside Biosphere a tremendous amount. Now, one thing I want to make note of is that I didn't talk anything about it, is that you have this interconnecting steel pieces that make up the superstructure or the space frame of Biosphere 2. And then laid or inset on top of those is you have these glass windows. And those glass windows are then caulked in with a material made by a company called Dow Corning. Now, the glass is made up of two components, a polybutyl vinyl and the glass itself. When you have those two materials, and again, it's a layer, it's glass, the polybutyl vinyl, and then the glass, they are adhered together, so there's no air void in between them. It's actually an adhesive that holds those three materials together. Those materials actually cut out virtually all UVA and UVB. So there's no UV or less than 1% that is transmitted through Biosphere 2. Because you have that overhead structure, you also do see a bit of light reduction from what would be a maximum value outside to the value that you receive as you go inside of Biosphere 2. So that's something that has to has to be considered when you're looking at. But again, we have not seen limitations in plant growth. We have not seen a significant impact in like the far red ratio. The UV spectrum is one that is of interest because, for example, nitrous oxide that is naturally produced, for example, in mangrove systems or in some of these aquatic systems, it is not naturally broken down inside biosphere 2. This is something that is photoreactive outside, but inside biosphere 2. So it's allowed to rise up, and it gives an opportunity, for example, if you're interested in some of these trace gases, to understand its natural production, because we know nitrous oxide and its derivatives, especially in the upper atmosphere, are considerably more reactive, for example, than even CO2. So understanding its production, you can use biosphere 2, and some of our researchers have done some very interesting things. Now, how do we control what goes on inside? I should have included a slide that shows you underneath all those vegetation areas of the ocean and everything, there is a basement area, if you can imagine it as such. We call it the technosphere. And this is where all the mechanical, the electrical, and the plumbing run. And you can think of it as sort of these large hallways underneath of all of those plant communities. And these air handler units operate on what we refer to as a closed loop. So we have an external power plant to biosphere 2. The electricity comes in. It then runs boilers or chillers. Those are going to heat and cool water. That water is sent over in a series of pipes that are, again, are sealed. They run through, if you think of like a large radiator on a car, these radiators that are inside of these large air handling units. And depending on what conditions you want to achieve in a particular biome, if you want to warm it up, if you want to cool it down, you're going to add the corresponding water to that coil. Air is pulled with a fan over and across that coil. You have an energy transfer, and then it is redistributed to the region. So you condition it as well as provide circulation with these large units. And we have 26 of those air handlers that are spread throughout the basement. And each of them or groups of them have specific set points depending on the area that they are responsible for controlling.
Oh, thanks very much, John. And we are getting a lot of questions and comments. So before I continue with the reading them, we are joined by Doctors Araxi Urrutia, who is the president of the Universities for Science Consortium, and by Constantino Macias, who is the director of UNAM Canada. Both are also researchers at the Institute of Ecology, so it's very handy. So, Araxi, Tino, do you want to make a comment so I can try to make order of the different questions and comments? Araxi, Tino?
Sorry, Araxi indicated that I may start. Thank you very much. Thank you, Jaime, and thank you, John, for such a lovely tour through the history and implications of the biosphere 2 and whatever takes place inside. Yes, indeed, I have a couple of comments more than questions, but perhaps you can expand on them. Yesterday, we heard in the news that the Earth may have breached 7 of 9 planetary boundaries, and that ocean acidification is next and is very close to be breached. That is, these thresholds are points of no or very, 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 very difficult return. And you mentioned that Biosphere 2 was a pioneer in calling the attention of some of the consequences of ocean acidification. So perhaps you could expand on this very crucial and very actual problem. But also, before you do, I wanted just to mention one other thing. Is you compared, I think it was a very pointy comparison of the hadron colliders and the mega 7 mirror telescopes, how the prices, the cost of building and running that type of facilities, which are fundamental for advancing knowledge, compares to the building and running of facilities such as B2, which is or potentially even more important for understanding how are we going to survive on Earth. So I mean, Mexico has been fiddling with the idea of building a hadron collider, and that is extremely expensive. I imagine that research on biospheres is cheaper in comparison, but can you tell us something about it?
Sure. Well, thank you very much, Constantino. And so obviously I'm biased. I will start with that from the, fundamentally, I think understanding diverse systems is critical. We were fortunate that Biosphere 2 was built in the private sector in late 80s, early 90s. The dollar amount at the time that it was constructed during that period was right around $250 million. So if we use inflation, we are, I'm sure, north of $1 billion today. I obviously believe that we need to take the lessons learned from Biosphere 2, the importance that we see with the number of research projects and publications that come out that have given us much greater insight into some of these fundamental mechanisms that tie Earth system processes together, to look to build that next generation of tool like Biosphere 2 that's going to improve and build on what we already know, but give us greater insight into these Earth systems, because we need these types of tools to be able to elucidate what is happening worldwide and to be able to show people the consequences. Because the exciting thing for me about Biosphere 2 is it's essentially a time machine. So we can talk about increases temperatures, we can talk about droughts, we can talk about ocean acidification or increases in coastal water temperatures. And yes, we can see in many cases those consequences, but it's only after those consequences have manifested themselves do we actually then visually see them. And then people go, oh, maybe we should have done something. And like you said, it's very, very difficult in most cases, if not impossible, to come back from that. With facilities like Biosphere 2, we can actually create those conditions before they happen and have a higher level of confidence that this is what's going to happen and show exactly what is going to happen. And I think in part, that is a true value of Biosphere 2. But fundamentally, I think Biosphere 2 is, if you think of it as a tool in your tool belt, you need many different types of tools to understand what's happening with Earth systems as a whole. But we are, I think, one of those very unique tools that there are none of them. There is no facility as large as Biosphere that's dedicated. There are huge greenhouses. They're primarily dedicated to cultivation. There are very sophisticated mesocosm experiments throughout the world. They're considerably smaller than Biosphere 2. So Biosphere 2 is unique in that it's one of a kind, and I think we have an opportunity to continue to use it and hopefully show the world and the different governments and administrations within various universities that it's these types of facilities that we're going to need to look to build. And I agree with you there. I don't want to take away the importance of understanding, the atom and the fundamental building blocks of it, looking to and further in space, because we can learn more about how our planet was formed. And we hear about that all the time. But I think it's facilities like Biosphere 2 that are going to potentially give us an opportunity to adapt to these very dramatic changes that are going to impact all of our lives, because we all benefit from the advancements, for example, in hurricane prediction and the pathways that they're going to take, rather than just waking up one morning and finding it on your doorstep, right? Same thing with our systems. If we know what's going to happen, then at least we can hopefully prepare. We may not be able to stop it. We may be at a point, but we can look at how we can adapt. And then hopefully, by showing that these conditions are coming, drive policy so that they don't actually come to fruition.
Yes.
Hey, Araxi.
Hi, John. Many thanks. It's a fantastic talk. I was wondering whether, and I would imagine it would be more so the case at the beginning when all those species were transported into Biosphere 2. But have you had any extinctions
That's a great question. And I think one of the benefits that we have, the fact that the facility is 35 years old, as a point of reference, the rainforest has been one of those systems that's probably been most closely watched and surveyed over its life. And when they originally planted Biosphere 2, and actually all of the systems, they did what they referred to as species packing. And so they put in as many species as they could in those different systems, both flora and in some cases fauna, although the fauna was really not large vertebrates per se. Like our rainforest, you're not going to see a jaguar walking through or large groups of birds or primates, for example. But when it comes to plants, the rainforest started out with 400 species. They knew that there was going to be loss. And what they had hoped is when the system stabilized, that you would still have a relatively diverse and functioning community. And I will tell you that early on, many ecologists said that Biosphere 2 would not work, it would not self-organize, and that everything would die off, or it would die off or organize in a way that it would not resemble any type of a natural system we have on the outside. So I'm not sure. I know when I was a kid in, I don't know, 7th or 8th grade, they had us make bio bottles where you take a 2-liter bottle and you put things in it. Well, some of them work brilliantly, and some, like mine, look like you can't really tell what's in there. There's this algal mat, right? So there were a lot of people who said that that was going to happen with Biosphere, and it didn't. So today in our rainforest, as an example, we have 100 species interacting. So we've gone from 400 to 100. But what we saw is that loss is not something that's been gradual over time. It's that hockey stick curve where all of the loss was very early on in the first 2 to 3 years. And then in these out years, we have a very stable community and we have very little loss and change in the community. And I think that's the significance, that even if you go and build a facility like Biosphere 2 today, that it's going to take a period of time for that stabilization to be reached, so that then you can conduct experiments and know that those experiments and the perturbations that you are creating are resulting in the changes that you see, and not that the system is still going through some stabilization. So I think that's where Biosphere 2, even though it's 35 years old, is uniquely positioned, because we are at that stabilization point. We know what our communities are, and we don't see them changing very dramatically. But that's a great question, and something that, it was a challenge that they faced with. But I think what we see today is that even though we've had significant loss in all of those systems, it hasn't been so much so that it's just, for example, a monoculture inside. There is still a diverse community that is interacting with one another.
Thank you. And my second question is, when we compare psychology research, experimental psychology research carried out with pigeons and that carried out with mice, the mice have a very fast generation time, the pigeons not so much. They are also more expensive, and so they tend to be reused for several consecutive experiments, not always in the same order. Whereas the mice, the usual thing is that they participate in one experiment and then you swap the mice for new mice. And so the mice people criticize the pigeon people because they think that the pigeons are not pristine anymore, therefore they are contaminated by the previous series of experiments they've participated in. And my question is, with Biosphere, you cannot, obviously you cannot just clean the slate, replant everything, and then do the next experiment. But how much of an impact, of a permanent impact, you think it's going on after doing each of the experiments?
That's a great question. So you're right. Biosphere 2 is an N of 1. So we don't have multiple rainforests. Leo is the exception, the Landscape Evolution Observatory that's built in triplicate. So we have 3 of those slopes of what you saw. But for the rainforest, for the ocean, the mangrove. And so what we've done in particular, for example, in the rainforest, in the CO2 experiment that I mentioned, is we do what we call a time series. So we'll start with the initial value, and then we'll ramp the system up, for example, from 400 to 800 to 1200 parts per million, but then we'll come back to 400. And what we hope to see, and what we've seen in our system, is that the A and A prime, the 400 that we started with and the 400 that we return to, the system's characteristics and response is the same. And we are limited because we don't want to do experiments that are going to completely desiccate or kill the system. So we can't push it to the brink, but we can push it nearly to the brink. And we do look at sort of our pre-experimental conditions and states by closely monitoring that. And then we look at our post. Once the system is returned to what we believe is as close to that original state, and how closely do those two conditions overlap. And so we have not seen very dramatic differences between the start and sort of those end conditions. And so we use that as at least a benchmark to say that we're not pushing them so far that we're seeing very dramatic changes. It's not perfect. I completely understand that. We only have an N of 1, as I mentioned earlier. And so those are experimentally some limitations that have to be considered when you're designing an experiment in bias for 2. And I think, to your point, it's crucial to understand that although bias for 2 is unique and it offers experimentally some really unique opportunities, it is yet but one tool that we need to use, and it's not the end all be all. And so it's collectively research that everybody is doing in these areas that is needed to be pulled together to understand, how to better understand the challenges that we're going to face in the future.
Thank you.
Well, we have some somehow related comments and questions. One is about the microbial communities. If are there studies on metagenomics or well, they ask about long-term experiments.
So no, that's another great question. Unfortunately, I will fully acknowledge that when bias for 2 was originally started, there was not a lot of discussions about sort of microbial community. So 35 years ago, very few people were talking about the microbiome. It was just sort of coming up, and they eventually discovered the soil was very influential. So we don't have a lot of that initial baseline data to be able to compare against. There have been groups that have come in and looked at the current condition of bias for 2. We do have some very basic data where we've been able to do some comparisons against, but it's not nearly as sophisticated as what we can do today. Now, what I can say, the one system that is different than, for example, the rainforest, the savanna, the ocean, the mangrove, the thorn scrub, and the desert is the slopes of LEO, the Landscape Evolution Observatory. So when that material was collected from northern Arizona in the crater, it was actually started out as very large particles or pieces. It was crushed or milled down to its loamy sand consistency and then deployed on the slopes. And what we did is we did have a microbial person look at and take initial samples, and that system has been periodically sampled through the time frame that it started to where we are today to understand how things have changed over its duration. We recognize that as an important condition. We do have people that are looking at the metabolomics and other components of it, but again, a lot of it is starting from a relatively current state and then moving forward. So that's where we currently are, but we do have people who have looked at that. And again, LEO has been one that has been more closely tracked just because that type of analysis were available at the time, and those types of considerations were made, and so we were able to take advantage of that ability.
Oh, thanks. Well, I will read some of the comments and questions. Veronica Cerrilla, well, congratulations, an amazing presentation. And she comments that we as individuals are like small sand grains, and in a complex society. And she makes a comment that we are like a sand storm against our own earth. Okay, thanks. Marcela Elizalde asked about the technology. How are the technological innovations? So how do you decide which technologies are more appropriate for biosphere 2 experiments?
Yeah. So I don't decide. We actually have a science advisory board, and we have a group of people who will take into consideration major changes and or experiments that are being proposed inside Biosphere 2. And then each one of our systems that I had an opportunity to talk about has a director associated with it. So the rainforest has a research director, the ocean does. And so they are the individual who really ultimately, as they say, the buck stops with them. They help to determine what experiments they want to do in there in conjunction with our science advisory group. When it comes to additions, technologically, we are always looking to take advantage of new technologies that can be deployed inside Biosphere 2 to improve our understanding of what is happening. Some of those considerations is how difficult is it to deploy? Can you go in and easily repair it, remove it, add new? In some cases like LEO, when you bury the sensors into the soil, we did not want to have to dig them up, disturb the soil, and put new ones back in. So we had to anticipate what the life expectancy would be, what the average failure rate would be of those sensors, and deploy them in such a way that even after a relatively long period of time, 10, 12 years, we would still have enough sensors within that soil profile to provide a good picture of what is happening. We can't do a lot with the exterior of the structure. We can't, it would be cost prohibitive, for example, for us to change the glass. I mean, ideally, if you had something like quartz material that would allow the full spectrum, you could then have a much wider spectrum that would be transmitted inside of Biosphere 2, and there would be advantages and disadvantages. But that's, for example, a material advancement that at least right now we wouldn't be able to realize because of the expense with it. But on the other hand, how do we control what happens inside? So there's obviously been significant advancements in these types of control softwares. And so we've been able to implement control software inside. And in conjunction with that, the nice thing is that we've been able to work with folks in our mathematics department at the University of Arizona to look towards implementing more refined and automated control in the sense that we're using AI to make long-term projections and anticipate what the conditions and how the conditions are going to change, and to be able to then use that machine learning to manipulate the instruments or the control devices to create the conditions that have been specified by our research directors. And so, that's a nice opportunity to work with groups to improve the control inside Biosphere 2. And that's a relatively new, these types of technologies are much newer, and they refer to that as SCADA. So that's your supervisory control and data acquisition system. And so we are looking to basically layer on our ability to control conditions by taking advantage of some of these technological advances. But, we have LiDARs inside, we have hyperspectral and infrared cameras that we can deploy in different areas. So different technologies are deployed in different ways, depending on what the desired outcome would be. And a lot of that is driven by our collaborators or our research directors or a combination thereof.
Okay, thanks. Angeles Pizza. I am a Mexican PhD engineer student, fascinating the engineering design. Thanks. And she asked if you can comment on what has been the most difficult, critical challenge in keeping the systems working. Yeah. How do you manage to keep Biosphere alive?
Yeah. So I would say that, relatively speaking, the terrestrial systems have been, I wouldn't say easy, but it's been, easier to keep them alive, maintain the conditions. When we look at that ocean system, that 2.6 million liter tank, any of you who are on this call who have had an aquarium at home, how finicky those conditions can be, whether it's maintaining pH, water quality, light. And so the ocean system, early on for the people who originally designed and built it and then were living inside, it was a challenge for them. And it took some time for the system to stabilize. Today, it is still one of those systems that poses challenges. And from an engineering perspective, think of it, we have an outdoor environment inside. And so all of the complexities that come with, we know what external conditions have and do to whether it's vehicles, whether it's building surfaces, and how materials succumb to those conditions. Well, now you put that inside of a building, you have a large saltwater tank in this particular example. I mean, it is extremely hard on the supporting members, and we have to regularly change those because they become severely rusted because of the salt, regardless of the material coatings that people put on things. It seems like very few of them ultimately can resist the corrosive nature. The mangrove system, a lot of those plants have adapted over time to exude salt from their leaves or glands that they have on the leaves. Well, you got to make sure that you keep those leaves cleaned off of the structure and they don't fall into a crevice and sit there, because then they are heavily loaded with salt. And it's just like pouring salt, for example, on your structure, and it has issues. But I would say that the aquatic environments have been the most difficult to control and maintain for the life of Biosphere 2, just because it's a bit more challenging to make sure that you properly maintain water chemistry. And think about Biosphere 2. So if any of you who have been to an aquarium, most of those aquariums are doing many are located on coastal areas. So a lot of times they can do large water changes with the water that they get from the ocean that's just adjacent to them. Biosphere 2's ocean system was originally seeded with some water from the Pacific Ocean off the Scripps Pier near San Diego. But it hasn't had a water change in its life. And so it's taken time for the system to stabilize, for the microbial communities to establish in the sand that makes up the benthic level in there. And so we think that benefits, but it's also one that from a fish perspective, you're going to look at it, and when you look, you're going to see fish, but it's not like that if you went to an aquarium where it's teeming, because you're going to have considerably more filtration to deal with that nutrient loading. And in our particular case, we found a nice balance because we don't feed the fish in our system. Any of the animals that we have, whether it's the insects, the few birds that are inside Biosphere 2, there are a few reptiles and amphibians, although they're very, very limited in number. They're dependent on what they can find inside. We don't feed anything to any of those organisms inside to keep them alive. And so they're dependent on what they get from the natural systems. But the aquatic systems are the hardest to maintain.
Thanks. Well, Francisco Rodriguez comments about climate change. You already made comments about the unique location in the Arizona desert. So thanks, Francisco. Gabriela Cortez makes related questions. If you were tasked with building Biosphere 3, where and what will you do?
Well, I mean, I think, Biosphere represents just, a very small fraction of those types of systems that you find throughout the world. We don't have a conifer forest, for example. We don't have an Arctic tundra. There are many, many systems that play crucial roles in our systems as a whole that we are not represented. So if I was to build another biosphere-like facility, then I think, I would actually look to have regional partners in different parts of the world to leverage the natural conditions that they have to construct similar facilities, but then to incorporate those biological communities that would be more appropriate given the region. And then, we could have a much broader representation of these complex systems in a highly controlled manner to be able to experiment with. And that's actually something that our director, Joaquin Ruiz, who has been looking towards, is creating a consortium where we can leverage what we've learned from Biosphere 2, the opportunities that we see with a facility such as Biosphere 2, and how do we potentially deploy that in other parts of the world with other institutions to leverage those unique conditions. So I think we're seeing that. And then a person who I originally worked with when I started at Biosphere 2, a gentleman by the name of Dr. Guanghui Lin, is Chinese, and they are actually looking at building some larger biospheres. And we've heard their plans, but I don't believe that anything has been formally initiated, and it's only at a concept stage. So there are people who are looking to try to leverage this type of technology, these ideas, to create that next generation of tool to give us insight.
Thanks. Well, we have several questions about the initial experiment with scientists living in Biosphere 2. Some, you mentioned it at the end, this new DSAM research experiment with new groups living in Biosphere 2. So I think we're more or less commented on this. Jessica Ramirez asked what were the major problems faced by the scientists, if they were related to the experimental facility or to the group itself.
That's a great question. So, originally when they sealed those 8 people inside, yes, there was some challenges because they didn't appropriately balance, we'll loosely term it, the biology inside. So we heard about oxygen going down, carbon dioxide going up, primarily driven because of soil respiration outpaced plant photosynthesis. The other challenge that they faced is, even though that agricultural area was considered to be one of the most highly productive equivalent agricultural areas anywhere in the world, it still did not produce enough calories for those 8 people who were inside. So nutritionally, they were okay. They were calorie deficit. And so, you're having a little bit of difficulty breathing, you're hungry, but there were group dynamic issues. So you think, if I took 8 of you on this call and said, okay, we're going to stick you inside a facility like Biosphere 2, you're going to need to be dependent on one another. You're going to have to live together with one another. You're going to have to work together. You're each going to have to pull your weight and do your part. And you're going to have to do this for 2 years. To think that there's not going to be conflict, to think that one person isn't going to get on the nerves of another, those things happen. And that has been really well documented over the years with a number of social and psychological studies by a wide range of institutions. It's been done, it's been looked at by NASA and other space agencies that look to put astronauts in space in teams for long periods of time. And so assembling a team that is in a high stress state is always a challenge. No matter how much screening you do, how much upfront, it's still difficult to replicate what is going to actually be experienced when you're in those situations. And so that was another compounding issue for the 8 people who were sealed in Biosphere 2, is that they ultimately couldn't get along and couldn't agree. And although it wasn't horrible, there was still a splitting, as I understand it, of the group. So there were 4 who believed you should sort of do it one way, and there were 4 that believed you should do it another way. And they didn't agree and get along. And it was relatively contentious. But again, I think that is human nature. When we you think about all of the different shows that are out there, that just the interactions that we have, in groups that we have on a daily basis, and how that it is a challenge to find a balance. And there's always varying personalities. And again, it's difficult to get everybody on the same page consistently for an extended period of time. And that was a challenge that they faced. So it was not trivial. They were able to stay the 2 years, but it was something that was a driving factor when they were inside.
Thanks, John. And Costantino, Araxi, do you want to make some comments to close the presentation?
Well, I think it's been a great talk and a very interesting discussion about a range of topics. And I think I will just join the call for greater international involvement and more cooperation in order to build facilities that are comparable to each other, but also at the same time more representative of the local conditions. I think that's a take-home message for me. I mean, it's a very nice facility, but we need many more of them.
Yes,
so
and the Biosphere 2 is a welcoming facility, so I think will be interesting to have more international collaboration. Sorry, Constantino, please.
No, sorry, I was getting in your way. So yes, I obviously agree. I dig up some data. Yes, it is building a biosphere 2, like 1 billion, is about a fifth of what it would cost building the Hadron Accelerator, or half, or a bit less than half, of what it would cost building another Magellan telescope. I think we need all of them. We need more Hadron accelerators. In many other countries, we need more telescopes to complement our view of the space, the universe. But we also need more biosphere 2s, and I think it is worth. They are relatively cheap compared to the value. They are good value for money. And if they cannot be built, they can be at least, so B2 should be incorporated into other research programs, be them small biospheres, big biospheres, or whatever, or even outdoor work, so that we collect a better understanding of our planet and how it works. That would be my take-home message. Thank you.
Thanks, Constantino. And well, we have just congratulations from Silver Rose, thanking for make this presentation available also to students. Veronica Cerrilla, congratulations to you and the Arizona University. Thanks to the Mexican, to the UNAM centers abroad, to UK, to Canada, San Antonio, Arizona, Tucson. Thanks to the red de divulgación científica del Estado de Hidalgo, de Coordinación de Colima, Instituto de Química, las ENES. Greetings from Gabriela Martínez from Puebla, Carolina Mora from Ensenada, Olga Sánchez, Guanajuato, Marcela Elizalde, Alatorre, Veracruz, Susan Morales, Nautla, Iván, many from Ciudad de México, Juan Herrera, Esperanza, Pati Hernández, Gerardo Romero, Ernestina Pérez, Graciela Valencia, Daniela López, Adriana Arellano, Carmen Monroy, Xochimilco, Guam, Yamil Rubio, Nahual Tlaxcala, Vega from Hidalgo, Randy, Politécnico, Daphne Canto, Yamil Rubio. Thanks and congratulations from Lilian Paola from Colombia, from Cali, Ayala from Paraguay, and many others. Thanks to all of you for joining us, and for the comments, and congratulations to John. Well, John, do you want to say some closing remarks?
No, well, thank you very much for this opportunity. I'm glad I had an opportunity to share with you a little bit about Biosphere 2. If you would like to learn more, our website, www.biosphere2.org. You can find me on the website. I'm happy to answer any questions that you may have. Please send me a note. We have a great team of research faculty. So if you're interested in a particular area and you can't find that person to connect with, don't hesitate to reach out to me. and I will get you connected with the appropriate person to answer your question, or if you're interested in collaborating and doing an experiment here, because we just touched on a few of the experiments we're doing. There's many more opportunities, and if you see an opportunity, we would love to hear from you and see how we can further the use of this remarkable facility. So again, thank you for this opportunity.
Thanks very much, John, and we look forward for having a next following up a presentation on the research projects. Yeah, we extend the invitation to the students and to colleagues to join us in Biosphere 2. John close the presentation with a short video clip, but there are many other videos and documentaries on Biosphere 2. So if you have time, it will be really interesting, and you will appreciate why we are in love with Biosphere 2, and why John has been there for several decades already. Yeah, it's a unique and a beautiful location in the Arizona desert. So thanks very much, Constantino, Araxi, and to all of you. And please join us next week for a presentation by Greg Barron on the agrovoltaics, a unique experiment also in Biosphere 2. And John mentioned that it has now extensive collaboration, including Mexico, Morocco, Israel, many other places. So join us next week for a follow-up on Biosphere 2. And hope to see you there. You can visit Biosphere 2, any of you.
Yes.
Listo, doctor. Estamos fuera del aire.